this video, we're going to continue multiplying polynomials, and today we'll be able to answer the second essential question. What are the special product patterns? So in our last lesson, we learned the different type of polynomials, and we learned about just multiplying any number of polynomials with any number of terms. Basically, we just use distributive property. Now, there's a very special case. Now, the special case happens anytime you have a binomial times a binomial. And what we've come up with over the years is this mnemonic device to help us remember how to distribute. So hopefully you all know how to distribute. And you're not really needing a mnemonic device for that. What I find this helpful for is eventually you're going to be given the final product. So let's just use the example above, right? Our final product where we had that 7-termed polynomial. You're going to be given that 7-termed polynomial, and you're going to need to get back to these 3 separate polynomials that were multiplied together, these factors. Okay, so eventually you'll be given the product, and you're going to need to get back to the factors. And so I think that this mnemonic device of FOIL is really helpful when we get to that. And we'll be getting to that shortly, not in this video. So let me explain what the first, outer, inner, and last actually represent. And again, we use this mnemonic device called FOIL. F for first, O for outer, I for inner, L for last. And really all it is distributing. So for example, let me rewrite these 2 binomials, the 2x plus 5 and the x plus 10. I'm going to go ahead and distribute those terms. So distribute every single term in the first polynomial with every single term in the second polynomial. But I am going to do it using the FOIL method. And you will see nothing is different. So first, F means first 2 terms. So the first terms in each binomial. So the 2x and the x, you multiply those together just like we've always done. I'm going to skip a little bit of space down here. And that's going to give me 2x squared. Now O, outer. You're going to take the outer terms in each binomial. So those are our outer terms. So in multiplying our outer terms together, and I like to kind of do it like this, but notice I would have just been distributing the 2x times the 10, just like I was before. I would get 20x. Then we move down to I for inner. Notice you'd be distributing that 5 to the x anyways, but our inner terms now get multiplied to give us 5x. Now the reason I like this is because oftentimes the inners and the outers are going to be like terms. So you add those together, you end up with a middle term of 25x. And then you move on to your last term. So you're just taking the 5 times the 10, just like you would have been doing if you were distributing 5 times 10 is 50. So in a way, when we're multiplying, I like to write it like this because it's kind of a nice shortcut. However, when you are eventually given this trinomial and you have to get back to what 2 binomials did we multiply to get this trinomial, thinking about outers and inners is going to be key. Okay, just remember I said that. Thinking about outers and inners is going to be key when we take this product, this trinomial, and try and separate it back into its factors of binomials. Okay, so let's do a couple examples of multiplying a binomial times a binomial using FOIL. All right, so I see that I have 2 binomials and I say to myself, hey, why don't I go ahead and use that FOIL method? It's basically just distributing like we were doing in our last video. So the first 2 terms multiply to give us 4x squared. And I like to skip a little bit of space because I'm not going to have to go back and combine like terms like I did before and rewrite everything out. I'm just going to have to combine inners and outers as long as they actually are like terms. Which is important that you write your binomials in descending order. And they are. I go from x to the first power to x to the 0 power in both binomials. Okay. First terms multiply to give us 4x squared. Now I'm going to go over to the outers, which is going to give me a negative 20x. Inners give me negative 7x. Add those together, I get negative 27x. And now distribute the last. So positive 35. Pretty simple. So notice, both signs on that last example were negative. And when you have both signs negative, you can remember this or not, it's going to be helpful again when we get to factoring, right? Or moving from this trinomial back to the original two binomial factors. Notice because my last two terms are both negative, my last term in my trinomial is actually a positive, and my middle term is negative. All right, so let's look at our next example. Notice both signs are positive in each binomial. Well, what does that mean? Well, let's go ahead and FOIL. Two binomials, I can FOIL them. I end up with x squared. Let's see, our outers will give us 3x. Our inners will give us 7x. Add those guys together. You're going to get a positive 10x. Last, positive 21. All right, so let's look at the signs again. So my last two terms were both positive, making a positive last term. And my inners and outers both were positive, making a middle term. That was also positive. All right, let's do another one. What happens when the signs are different in each binomial? Let's see. FOILing, I get x times x gives me x squared. Outers give me negative 3x. Inners give me positive 7x. Combine those, I'm going to get a 4x. And what happens to my last term? It's going to be negative. So anytime the signs in the binomials are opposite, you're going to end up with a negative last term or a negative constant. And then it's really going to depend on which number had the larger absolute value in inners and outers on what your sign of the middle term is. I can't really give you a shortcut for that. All right, so that was using the FOIL method. Pretty straightforward. You can go ahead and continue just using distributive property. The problem's going to be when we start factoring the trinomials and we got to get back to the products of the binomials, you're going to need to recognize the inners and outers. Now, there are some special product patterns that I really would encourage you to learn. The sooner the better. So, the first special product pattern is the sum and difference pattern. Notice in the sum and difference pattern, a plus b times a minus b, we have two binomials with the exact same terms. The only difference in those binomials is the sum and difference signs. And when you multiply them together, something really cool happens. So watch this. Let's do it with our first example. I have x plus 7 times x minus 7, right? I have the exact same two terms in each binomial. The only difference is the sum and difference pattern. Using our FOIL method, because I have two binomials, well, my first terms give me x squared. My outers give me negative 7x, and my inners give me positive 7x. What do you notice about the inners and the outers? The inners and the outers are opposites. They actually cancel each other out. They're gone. No middle term. And then multiply the last terms, and you get negative 49. We call this a difference of two squares because x is actually a base of x squared, and 49 is actually a base of 7 squared, hence the difference of two squares. Your actual answer when you multiply a sum and difference pattern is the difference of two squares. Okay, so if we go back up to our sum and difference pattern definition here, what you get right here is called a difference of 2 squares. Please recognize this. It's going to be very, very handy very, very soon. All right, so let's go ahead and do that now. I have 2 binomials, exact same terms. However, now I have a difference and a sum. You can still call it a sum and difference pattern, or you can call it a difference and sum pattern. But guess what's going to happen? Outers and inners are going to cancel out. You don't believe me? Let me prove it to you. So multiplying my first terms, I'm going to get a 4x squared. My outers give me positive 2x. My inners give me negative 2x, leaving me with no middle term. Those are opposites, right? They cancel out. Last terms multiply to give me a negative 1. This, in fact, is a difference of 2 squares, right? 4x squared can be rewritten as a base of 2x to the second power. And 1 can be rewritten as 1, the base, to the second power. It is the difference of 2 squares. It is literally a difference of 2 squares. So let's go ahead and let's highlight that. Let's use a different color. How about green? We get a difference of 2 squares pattern. Going to be super important moving forward. What I'm going to end up giving you in a future lesson is we'll give you the difference of 2 squares as the product, and you're going to have to factor it back into the sum and difference pattern. So the sooner you learn it, the easier it's going to be. All right, your next special product pattern is the square of a binomial pattern. Now this will change depending on what the sign of the binomial that is being squared. But notice for both of these, you have binomials that are being squared, right? A plus B is a binomial and they're squaring it. All right, so this becomes pretty darn tricky for some of you. I hope you're listening. Now this becomes really tricky for some of you. I'm going to do an example over here just to show you what not to do. All right, so let's do the square of the binomial. How about x plus 5 squared? Now, some of you guys will get really excited and you'll want to square the first term and square the last term and be done, right? Some of you will say, oh, I'm allowed to just distribute this exponent. There's no rule in math that says that you are ever allowed to distribute an exponent. Nope, you're only allowed to distribute some polynomial to another polynomial over addition or subtraction, okay? No distributing exponents. It doesn't exist. So what I'm trying to tell you is this is not x squared plus 25. It is not that. This is very bad. Don't do this. Notice what actually happens here. Let me go ahead and do this right for you. So x plus 5 squared is actually x plus 5 times x plus 5. All right, let's FOIL that. I got 2 binomials. So my first terms will give me x squared. And look at this. Outers are 5x. Inners are 5x. They are both the exact same sign. So we can double, right, either inners or outers, or we can just add them together to get 10x. And then last terms give you 25. So notice if I square a binomial, I end up with, and we call this a perfect square trinomial. This is correct. Okay, so these right here, let's see, let's go back, highlight, thought I did that. So those are our squares of binomials. And when we multiply them together, notice we don't end up with another binomial. We end up with what we'll call perfect square trinomials. I'll use a different color. These guys here, these are what we call perfect square trinomials. Perfect square trinomial. They always follow this pattern. the first term is always a perfect square. And I'll use our example that we just did here on the right. Notice my first term is x squared, so I can write that as a base of x squared. My last term is also a perfect square. Notice it's 25, which can be rewritten as 5 as the base squared. Now, if I take x and multiply it by 5 and double it, I will end up with, well, 5x doubled is 2 times 5x, or 10x. Now, because I had both binomials with positive signs, all terms are positive. So you end up with exactly what we got. So recognizing this pattern, if you have a trinomial, will let you know that if you're going to go backwards, like what's going to be happening in a future lesson, and you have to factor it, you would factor it back into the square of a binomial. Now, if you have a binomial that is the difference between two terms, like a minus b here, well, then your middle term is going to be negative, because inners and outers are going to both be negative. All right, let's do a couple of examples here. So, first example, x minus 7 squared. Notice it is a binomial squared. So really, there are inners and outers, and those inners and outers are going to be exactly the same, so you can double whatever the inners and outers are. Okay, so first terms, if I multiply them, I'm going to end up with x squared. Now, you take each term, multiply it by each other, and double it. So for my middle term, because there's a negative 7 there, my middle term is going to be negative. I'm going to take 2 times 7 times x, or vice versa. Again, in multiplication, order is not important. And then I'm going to multiply, or think about multiplying my last terms. Well, negative 7 times a negative 7 is going to be a positive 49, or in other words, you're going to need that negative 7 squared, right? So you're going to add 7 squared. Now, I encourage you to maybe FOIL this out like we did in this example with x plus 5 squared until you recognize this pattern. Practice it as much as you need. Okay, so our final trinomial is going to be x squared minus 14x plus 49. Notice the middle term came from taking each term in the binomial, multiplying them together, and then doubling it. So there you have it, a perfect square trinomial. All right, last example. So again, I have a binomial squared. So in order to do this, what we do is we square our first term. Now some of you guys will mess up on this. This is actually 3x that needs to be squared. Okay, we'll come back to that in a second. Now my sign between my two terms in my binomial is an addition sign, so my middle term will be positive. Because again, come over here to this x plus 5 times x plus 5, both terms were positive. And when we added them together, we got a positive 10x. If they were both negative, then we would have had two negative middle terms. Inners and outers would give us a negative middle term. All right, so back to this. So taking the first term times the second term and doubling it. So 2 times 3x times 4, right? 2 times anything is doubling it. All right, and then the last term gets squared as well. So positive 4 squared. Now what is 3x squared? So because I have a product here, everything gets squared. The 3 gets squared, the x gets squared. Okay, so we're going to go 3 squared, x squared, or really that's just 9x squared. I'm going to go ahead and write it like that. Okay, my inners and outers, if I had double distributed or FOILed this, I would have ended up with, let's see, 2 of the 3x times 4, which would give us 12x, double that, 24x, plus 16. And here you have it, another perfect square trinomial that came from the square of a binomial pattern.